We are developing techniques for embedded processing with particular emphasis on distributed power-constrained scenarios. There are several signal and image processing applications where minimizing power consumption is crucial. This is especially true in battery-powered or energy harvesting systems. We focus on both code development methodology and hardware design. The key metric is low power computation close to the data source itself. We've targeted FPGA technology as the most efficient solution in terms of computation per watt, as compared, for example, to single or multi-core CPUs or GPUs.
We aim to express an algorithm as a high-level abstraction and to easily translate it into executable code for an embedded sensing and processing platforms. We want to dramatically reduce code development time, yet match or even better handcrafted code. At the highest level, we have developed Ripple, a language for designing image processing systems for FPGAs and multi-core architectures. Ripple allows us to generate image processing hardware pipelines more quickly than through traditional methodologies. At its heart, there's a data flow architecture that we can leverage for power optimizations. Data flow encapsulates computations in actors, independent parallel blocks that can operate asynchronously, transmitting data across communication channels. We integrate the Ripple-generated pipelines into our smart camera architecture. Ripple source code is compiled by the ORC toolchain to produce application logic that processes the raw data from the sensor to create a smart camera system. These demonstrations show two examples, from simple edge detection to mean shift tracking. A key innovation in the latter is the data-dependent variable time complexity of the algorithm. This allows us to apply clock gating strategies, transformations at algorithm and implementation levels, and explore the solution space. The natural progression of this research is approximate computing. Approximate computing abandons the idea of precise computations and instead focuses on inaccurate but good enough processing at a fraction of power consumption.
Approximations are typically performed at design time. A certain processing element, such as an algorithmic operation, is approximated and the output is compared against a baseline to determine quality. This significantly increases development time. In this example, we focus on runtime approximate computing. Assuming that circuits have several approximation levels, we develop techniques for determining at runtime what is the appropriate level to use. This is done by incorporating prior knowledge about the application at hand, by evaluating statistical metrics of the target output, which we can dynamically monitor at runtime.
We are currently trying to establish models of which approximations can be performed as a function of the several algorithmic parameters and their effect on metrics for evaluation. However, using software and hardware approximation to save power for remote distributed sensors changes the mathematical assumptions. Solving this problem is a key challenge for future signal and image processing research.